So today we're going to talk about something that I haven't heard anyone else talk about, and it's something that we've been noticing, and Kevin and I have been wanting to put this one into existence for quite a while. But I want to talk about ram air wing wear and tear. Hopefully not tear, because we don't want to push it to that point, right? But we all know people have torn their parachutes or speed wings. And I think you're going to be really surprised as to what you think wears parachutes out actually isn't. And we've learned this in the last few years, both in paragliding and skydiving. So I'm going to tell you a little bit about how the fabric's made. We're not really going to talk about lines. This could be mostly a fabric and tape, like the wing itself. How does this thing wear out? How it's made, how it goes together, the materials that get used, what wears, what we normally look at, what we all talk about, and then what's really going on. And it is actually surprisingly different. And then what we can do to minimize some of this, right, and make things last a little bit longer. That's a little bit less of this, but if you understand the mechanism that your wing wears out with, you can automatically adjust how you treat it, so that you can make them last longer. So I'm going to go through this. You guys get the normal background, like, okay, why should I be talking about this stuff? You guys all know me. I'm not going to spend a lot of time on this, but I've been jumping, skydiving, engineering, designing things for quite a few years now. I don't just design the stuff, I actually use it. I'm out there jumping still every week. Flying the high performance and the low performance. In the last week, I've skydived and paragliding. I've been flying speed wings. I was out in Utah last week. So Kevin and I are both out there doing these things. So I'm not telling you this is some guy who's got a company. I'm telling you this is a guy who's actually using this stuff. So fabric. That's, we're all using fabric, right? Paragliders and parachutes are essentially the same fabric. They may not feel the same, but they're all essentially the same fabric. And something you might find surprising is the ZP fabric and like our FT30, the fabric part of it is the exact same fabric. The only difference is the post-processing after it's been woven, right? But the fibers and stuff, they're all born and created in the exact same way. They're 6.6 nylon. So nylon is, there's different grades of nylon. Let's see if we can get this a bit better. A little better focus? Maybe not. Well, we'll have to go with that. So that 6.6 is the fiber. So there's different grades, right? So if you go on the internet and try and buy nylon, like you go to Ripstop, buy the roll and stuff, you're going to find nylon that's fiber 6.0. That's not what we use in paragliders and parachutes. It's 6.6, right? Typically they're woven in 30 denier, which is 30D. And that ranges depending on how they weave it and the weave pattern, anywhere from 28 to about 40 grams per centimeter squared. So stuff, and that also varies with the coating. So denier is like a definition of the fiber. So when you're talking about denier, you're using like the thickness of the actual fiber. That's what you're talking about. So like your lines, when they weave the lines, they have a denier of the individual fibers, or denier. The nylon is as well. So this is actual pictures of the testing equipment at the plant that we use, because we've audited our plants. So they're all woven with a ripstop, and the ripstops are a little different fiber, right? And it's the fiber it's a little tougher, and the weave is a little bit different. It's a little tighter weave, and it's meant to stop any tears, right? So it prevents it from spreading to the next group over. So the fabric's woven, and then it goes through a calendar process. Does anybody here know what a calendar process is? So that's probably the coolest part, and it's probably the biggest innovation that we've come up with in fabric for the skydiving stuff. And it's like your rescue fabric, reserve fabric, or what you probably refer to as F111, which is actually a brand name. It's a brand name that's no longer available. It's not an actual process. That's calendared fabric. So it's just nylon that's woven, and then it's calendared. Calendaring, I'll talk a little bit more in the next couple slides, but essentially it flattens the fibers. And calendaring helps drastically reduce the porosity initially. After it's calendared, and it may be calendared one time, it may be calendared 10 times. Depends on the manufacturer, depends on what you're after. Then we apply coatings. So trying to get a little bit better focus. Sorry, guys. Is that good? Okay. So we may apply, there's primarily a couple different coatings. Well, during this process, you can see here, there's a tensile tester over there. There's a UV tester. There's a tear tester. When we have our fabric made, every roll gets checked at every step of the process. So it's kind of neat. There's a little conveyor belt with little hooks. So they weave it, they cut off a sample, put it on the hook, and goes right into this little room where they porosity test it, they UV test it, they tear test it, and they tensile test it. Then it gets calendared, goes right back in. Gets calendared again, right back in. Gets coated with silicone, right in. So every step of the way on every single roll gets checked and checked and checked and checked, which is kind of cool. Not every mill does this. These guys are pretty sophisticated and they're really big. This is a calendaring process right here. You guys don't want to hear us talking about how cool it is and nerding out. So calendaring takes it, rolls it up, puts it up through giant heated drums, and they're pressing together really, really hard. And what this does is it reorients the fibers and pushes them together, but it actually flattens each fiber. So they're, instead of being a completely round fiber, it flattens them. And when it flattens them, they spread out and they fill out the gap between the weave. It's really effective. Like our F111, our rescue materials, are basically only calendared. Our particular supplier will calendar some fabrics, I believe it's up to 10 times. Yep. So your average, I think, is like 4 to 6 on like a ZP. But it just depends. They're looking for a particular thickness, profile, and density, and fiber density. So they're not just going to calendar it. No, we always calendar twice. They calendar until they get the desired result. So calendaring is kind of, it's a really neat process. It's something that everything gets, right? So ZP gets calendared first and then coated. Rescue or F111, it's also referred to as 0 to 3 CFM material. It's 0 to 3 cubic feet per minute. That's the PIA spec. PIA spec would be 0 to 3 CFM type 4 is usually what's used. That dictates the porosity and the tear strength. Typically, it's uncoated or coated depending on which spec it's done. Some of the F111 and the type 4 fabric has a chlorofluorocarbon coating. We're trying to get rid of that because it's not great for the environment. It gives a little water resistance. It's not much, and it's meant just for like a preservative, right? A lot of the mills don't want to deal with that stuff anymore. The other thing we're seeing is that in Europe, there's some new environmental regulations that mean you have to take PFAS, and some of the coloring stuff is on lines and sheathing and fabric. You can no longer use some of these coloring stuff. So we're seeing some of the formulations on the dyes and things are changing a little bit. But that's all done. So the dyeing is done before the calendar. You see that they're running colored fabric through there, right? So once it gets woven, colored, and then at that point, now you're calendaring, now you're post-processing. So then we coat it, right? So there's a couple coatings, 2 primary coatings that we use in skydiving. The number 1 is silicone. Everyone, that's ZP. It's the stuff the little slippery stuff. That's a siliconized coating. So that fabric gets, at least our spec, gets silicone on each side. It's double coated. In paragliding and some of our others, it gets a silicone and or a polyurethane. Sometimes it gets just a polyurethane coating. So polyurethane is the really thick stuff, the stuff that you feel it's really stiff. So people typically refer to sail fabric. They call it sail. It's kind of an interesting name because there is no such thing as sail fabric. You can't call any fabric supplier in the world and order sail. They laugh at you. It doesn't exist. So we have to stop using that, right? There's polyurethane coated fabric, and then there is a wide variety of this stuff. Some of the stuff that if you order sail fabric, you're actually going to get an epoxy coating because the stuff that's used for spinnaker is no longer this stuff. So we need to stop using that term. There is no definition of it. There's no specification for sail fabric. So just a side note, typically our FT30 is a siliconized polyurethane coated fabric. So it's getting different coatings on each side, and they're both a mix, right? It's a kind of a special formulation. This is a coating machine right here. So cool. Just gets there now. So it just runs through it, and sometimes they run it back through. So again, they're checking all the parameters each time. See, it goes back through, it gets coated, then dried, and then put back onto another roll. So if you could see here, this is kind of, and this isn't super great, but what you're going to see, the calendar here, you can see up in here, and what it's done is there's groups of fibers in each of these, and they've all been flattened. And I guess you guys that are here, if you really want to see a better view of it, you can take a look at it on the web, or I can show you on my computer screen. But what you can see is in each of these up here on the upper part of the screen is there's varying degrees of flatness. And as you move over towards the right, the fibers have been flattened more and more. And what you'll see is you can probably even see it here, is if you look up here and in there, you can see less gaps between these fibers. The more flat they are, the more they fill out. Below here is the coating impregnations. And you'll see here that like the better the coating impregnation and the tighter the weave, the less gaps you get. But for example, here on this one, you've actually got a gap in the coating. So that's where permeability comes from, or porosity. Is small imperfections in the coating, small imperfections in the weave. Ideally, we're making this fabric as low permeability as we can get it. So when the fabric wears, anybody have an idea what the #1 wear is on fabric? Sun, right? So nylon is inherently UV unstable. It is not as good. There are other fabrics and other polymers that are better UV stability, but they don't have some of the other properties we're going to talk about in a few minutes. Nice thing about nylon is it's got a lot of the engineering properties that we really want for skydiving in particular and for paragliding. See on the right, here's kind of a fresh strand of nylon. This is a scanning electron microscope picture. I didn't take this. This is taken from a wear study. Harvard, some scientists at Harvard did some wear analysis on paragliding fabric, and they wrote a paper on it. And the last two slides, the slide of the close-up of the weave, and this are both out of that paper. You can see on the left, it's a robust fiber. It's fully intact and pretty solid, right? And then if you look over on the right, that's the part of the fiber that flashing out of existence. What am I doing? Okay. On the background. Yeah, keep moving.
Still see me?
Yeah, keep moving. So the one on the right is one that the UV is really worn out, and you can see it's not just that you lose like coloration and stuff like that. You've actually lost portions of the fiber. You lost density and stiffness. So it's the actual fibers themselves deteriorate. The matrix becomes less dense. You can almost feel it in an old fabric that you touch it and feel it. And it feels lighter almost. And that's what's going on is They're actually, it's almost like sublimation, kind of like some of the fabric is cooking off. Some of the parts of the polymer are cooking off. Um, it's not exactly what's happening, but it's a good analogy. So they took a couple different fibers, and the important part of this graph is to realize that they did a bunch of different um, uh, tests on them. Some of them were heat, some of them were cold. Then you've got UV and bending or flexure. And you can see that on each of these different samples, they all affected differently, but the only two that had a really big effect were UV and flexure. And bending, guys. Use. This particular paper was focused on a lot of permeability changes, and historically that's been assumed to have the largest effect. We all talk about permeability and everyone kind of assumes it comes from UV. The important thing to realize here is it's not just UV, right? You could jump your parachute only at night and the fabric is still going to wear, and the material is going to continue to degrade from flexure. There's also a small portion of the wear that just comes from time, right? Nylon deteriorates over time, not a huge amount. And in fact, I'm going to cover that in a future slide. But as the material ages, it does lose some strength. It's almost negligible for the periods of time that we would store gear, but it does occur. As the fabric, now that's in strength of the material, by the way. The permeability we don't have good data on. As best we can tell, the permeability doesn't actually change that much with time, just from storage. Permeability effects on wings. Has anybody here jumped a wing that's been started to get really high porosity? Have. Oh, yep, pilot chutes. They quit doing their job. So what's happening in the wing here inside? This is a CFD model with ANSYS Fluent, and it's from our Harvard study. I didn't get to do this because we don't have a Fluent subscription. But what the model shows is exactly what we experience. You see on this left one, the pressure is being contained very nicely. You look at the boundary conditions; they're really clean, right on this leading edge. You don't see any separation, vortices, stuff like that. What happens on the permeable fabric over here on the right side is it goes in, and then you see the flow lines. It's actually starting to flow outside, and then you see a separation on the leading edge surface there. Happens to be where most of your lift is produced. Most of the lift is on the front part of the wing, guys. The first 25% of the board produces probably 70–80% of the lift. Estimate, don't hold me to those numbers. It's just a ballpark and depends on the airflow, right? So can you imagine if the flow starts to separate in that critical section, what happens? Typically, you lose lift and you increase drag. What does that translate to you as the pilot? A wing with higher porosity starts to lose lift, and increase drag. So what's going to happen to your descent rate? It's going to increase, right? Because L goes down and drag goes up, and your glide ratio is L over D. So all of a sudden you start coming down faster. And then what happens when you go to add lift and stop that descent rate? You don't have as much. Yeah, so you don't get as good of flares too. So pretty common. I think we all intrinsically can kind of understand that. And I think it'll correlate to a lot of people's experience. They also did some studies on and some modeling on, well, when the fabric loses strength and is worn from flexure, what happens to the wing itself too? And the important thing to note here is you can see on the left that's a impermeable material subject to this one doesn't have flexure damage and this one does. And you can see that lighter color over the front part of the wing looks like there's less intensity, right? So that's a less a lower pressure zone that's not as big, because that low pressure zone is your lift. And so the lift is not as strong and more diffuse, not as focused, right? And so it really does, just the flexure changes actually reduce the lift capacity of your wing. So it could be completely perfect porosity. The fabric's been deteriorated from flexure. You actually will lose lift. Well, what does that correlate to? That's a lot like lift loss we got from permeability. So it's important to realize that this is kind of that aha moment, I think, that I want to share with you guys, is that the flexure damage on your fabric can be as great, or in some cases even a little bit more, than the porosity damage. So you could have a wing that has a ton of jumps and the porosity looks good, but it's the fabric's been flexed and you've deteriorated the fabric from loading it and wear and tear just from use, and the flight characteristics are going to change. So every time you use your wing, you're deteriorating it. And we'll talk a little bit about like how you use it and how that affects it. So the Army's done a lot of this, and they're trying to figure out, like, hey, look, what causes wear on our parachutes? Because they want to be able to buy a bunch, put them on a shelf, and then pull them off the shelf and go use them. So they want to understand, okay, what deteriorates it? And this is from that study, and they've watched parachutes over 20-year life cycles, right? And the one thing they found is, well, while nylon does have a slow deterioration of strength over time, they found that the single largest way to correlate strength and residual strength in nylon is how many jumps the parachute has on it. It's almost not, in the studies they did, it's almost not registerable. It is, but it's a very small amount from just sitting. It's really use. So the Army has found this on parachutes, and they found it in relatively low jump numbers compared to what we do as sport pilots, guys. So they've seen the same thing. Is there's your equation. They curve fitted it with strength deterioration on the nylon, and the two are tied together. So this flexural strength is tied to the strength deterioration. So it's a structural thing of the weave. We first noticed this. It became visible to us when we started load testing some of our paragliders. We've theorized a lot of this in the past and talked about it. And this is our Loki 217 we load tested. It's about 4 or 5 years ago now. And this is the first time that we could actually like see it in person. And Kevin brought this wing. We can kite it if you guys want, but you kite it next to an unload tested. At least we'll have an empty dumpster, right? So when you kite this next to an unload tested wing or just a regular flown wing, it's noticeable. And this is a brand new wing and it's load tested. So this is a certification requirement for EN. Right? You have to send your stuff over and they load test it, and depending on the type of wing, they may even flight test it. It's a whole other seminar on why we need stuff like that in skydiving. But this is what the load test looks like. And essentially they take it, hang it statically in a little bit of a headwind, and they've got a coiled up weak link on a chain or a cable. They send a truck driving on really fast. And the whole goal here is to generate an 800 kilogram load on the wing, 1,600 pounds, instantaneous. Your wing has to survive this and a static load test. Boom. That's it. Nothing broke. And this could be attributed, this could be something similar to like a really rough reinflation. Like if you took a tuck on a paraglider or something like that in turbulence and reinflated really quick. Or what else might be kind of like a shock load? An opening. Right, guys, an opening. This is actually a lot like an opening in a lot of ways. The wing flies pretty good still, but it doesn't look the same. And there are some differences. Like you fly them back to back, you does. That's one reinflation, right? So it matters. And that started us looking at a lot of different things. But let's talk a little bit about why this happens. Let me go to the next one. First thing I want to talk a little bit about is the fabric, how it's made. So we talked about the weave earlier, right? So I'm going to use some language here when we talk about it. But if you look at the weave, there's two different parts. They're woven perpendicular to each other. You've got the warp and the weft. So the warp is the fibers that go all the way down the roll of fabric. So the warp fibers might be a kilometer long. Sometimes it depends on how long the run of fabric is. Typically, we're buying fabric in rolls of 120 meters. Most of them, right?
Once they've been cut.
Yeah, once they've been cut. The missile roll might be 1,000 meters. Yeah. So then in between that, you've got the weft. That's where that shuttle shot through the weave. Depends. Sometimes it's shot with a jet of water. Sometimes it's shot with a jet of air. But they have a little shuttle and it shoots it between the weave. So it depends on how that particular mill weaves their fabric. The newer mills use an air fiber. Problem with that is shooting on a jet of air is that really have to control static electricity, right? So and humidity matters a ton. So we've been to a couple of different places where they're weaving fabric for us, but when it's shooting it through with the jet of air, it's a fancier, newer machine. They can control a lot of parameters better, but they end up spending massive amounts of money controlling the environment. Whereas the water jet ones, you don't have a lot of the static electricity and the other stuff that builds up, and essentially the entire factory is saturated with humidity. So it's a little more it's an older technology, and typically used in bigger mills. But it depends on what you get. So they shoot that back and forth, and that's your weft. So you got your warp is the long ways in the weft. And believe it or not, when we're designing the wings, we're picking warp directions. I specify on the design what's warp. Where does the warp run on my profiles, on my skins, stuff like that. That matters. It matters a lot, by the way, because the deformation in the fabric is different along the warp and along the weft. And then what else do we have here? Well, we've got bias. Bias is that 45-degree angle. It's not on the warp. It's not on the weft. Some fabrics, pretty good on the bias, pretty tight. Don't have that much deflection. Some fabrics have wild amounts of deflection on the bias, right? A little bit more technology, or a little bit more vocabulary here is the raw cut edge. You can see here we talk about when they cut those fibers on the warp. They call it a cut edge. The sides of fabric are called selvage, and some fabric that's a finished selvage, it's trimmed, it's nice and neat. Others, it's fuzzy. So it's a little vocabulary there. But the important thing to realize is fabric it's called a non-homogeneous material, right? Or non-isotropic, sorry. Steel, aluminum are isotropic. You load them this way, this way, this way, this way. They're essentially the same for all intents and purposes. The matrix behaves the same in all directions. Fabric is not an isotropic material. It behaves differently. So you load it on the warp or the weft, it might be one thing, and they might be different. You load it on the bias, it's going to be completely different, right? The other thing that's going to have an effect on those behaviors is the coatings. Because, again, fabric's the same, right? ZP fabric, our ZP and our FT30 are the same fabric. They come out of the exact same roll, and they just go to different coatings. So the coating affects those things as well. So for example, say something that gets a polyurethane coating might have a little bit stiffer matrix in all directions, right? You guys notice that our FT30 is kind of stiffer. Maybe feels a little bit thicker. It's actually not really that much thicker. We measure thickness on them. Polyurethane does add a little bit of thickness, but it's stiffer, right? So it's bigger. ZP, silicon's a really slippery substance. It might actually add some flexibility in some directions. So it's The coating matters a lot. So changes in material both result, they result from dimensional changes in the fabric over time. Our panels, so where's Simon? Simon, this is a panel out of your Odin. How many flight hours does your Odin have on it? 10 flight hours. So it got put into a tree by his buddy, and there was some tearing, right? This is last week. The panels were coming out. We're repairing it at the factory. And so I grabbed those panels in, and I don't know if you can see it on here, but you can see that I printed out those panels on a piece of paper to scale out of our CAD plans. And I laid these panels in, and you see I've taken them, I've taken a magnet here and a magnet here and stretched it so it's tight. And I don't know if you guys can see it, but there's the edge of the panel right there. It's supposed to show up right there. There's an edge. These two are forced on those edges. But what you can see is that the panel's no longer the same size as when it got cut. What can you guys think would be happening? There, non-siliconized and siliconized fabric and less PU. But the second it gets sewn together, how it gets sewn together, the panels change. And then from there, they continue to change. That's one of the dangers when you see that, like stuff like we say that when we replace a cell, we want to do it symmetrically, right? It's because when you sew the same CAD, same exact dimension as the original size, you sew it back on, the wing you're putting it back onto has changed shape over time. Those panels no longer match as cleanly as you would like. And so if you were to do it asymmetrically on the wing, there's a really good chance that part of your wing is not the same shape as the other part of the wing, and you run a chance of not having a symmetrically flying wing. So even just a few flights, this will show up. Did someone raise their hand over here? Oh, I thought I saw a hand go up. Okay. Siliconized fabric seems to stretch primarily, right? And that's a behavior we see a lot. PU, polyurethane, PU, is what we call it. Stiffer, but along the seam lines, we tend to, no, this is an important distinction. It's not the fabric panel as a whole, but along the seam lines, we tend to see a shrinkage. It presents as a shrinkage. So like an FT30 wing, if we were to try and put a new bottom seam on it, the seams don't quite line up as much. Part of this is a three-dimensional change because you've got the ballooning of each panel, right? So now the panels balloon, and that warp, weft, and bias dimensional changes may dome this panel, right? So the seams may actually change some dimensional stability there. This progresses over time. This wing is it's somewhere between 5 to 7 mils, and there's one spot where it's almost a centimeter different after just sewing and 10 hours of flight. 10 hours of flight might be the same as like 100 jumps where it's just a ballpark guess, right? So you can see that a relatively new wing is already showing these dimensional changes. We see this when we pull them apart. What affects these changes? What's the primary driver on it? Well, yes. Loading, yeah. So the higher loaded, the higher the deformation changes. Now, this is an important thing. It's stress that does this, guys. So it's not just that your 60 square foot HK2 shows it more. It does. So a millimeter of deflection on a HK260 will be way more evident than a millimeter of deflection on a prime 280. But pound for pound, you've put more stress because you're putting a similar load over a smaller area. Stress is force over area, really conceptually, right? So if you're putting 200 pounds under a 60 square foot parachute, you're stressing that fabric in a unit stress at all the attachment points, at the top surface, at the bottom surface, you're stressing the fabric to a higher stress. You take that same 60 or 200-pound person and you put them under a 260, where the deflections matter less, it's also stress less. So it's not a function just of size and sensitivity. It's a function of the load you're putting under the wing, because we're not scaling the wing loadings accordingly. It may be a 0.5 on a 280. You're at a 3.0 maybe on a 60. So you got to see that the wing loadings reflect a little bit of that stress that's distributed right across the wing. So small wings are going to affect. They're going to get a double whammy on these changes. A, they're stressed more, but B, they're also typically loaded the same or more than the other wings. You know, how many of these guys, like, I just pulled this off the internet. It's a Mr. Bill on a 60. Guys, you guys don't understand how we cringe when we see this stuff, because this is the worst thing you can do for the longevity of your wing, as far as loading it. God forbid you do this in a sandy environment after you've left it in the trunk of your car. And I probably just described a typical weekend for most of you, right? So this is going to make wings last shorter time frames. Let's talk a little bit about stress strain. So strain is how much it deflects, right? And stress is how much you load it. So for typical nylon stuff, these are nylons that we don't use. This is a 6.6 and a 10 fiber nylon, really similar. You can see that the stress strain, the important thing here is you load it up in here. This is called the elastic range over here on the left, where it's almost vertical. And any stress you put into it, if you take the load off, it goes right back to its original shape. Kind of a small region right there. Steel has a much bigger region. Steel and aluminum alloys, they got a nice gradual curve. And you load them up, they go right back to the original. Load them up, they go right back to the original. You kind of, when you're in that elastic range, it's a great spot. If we could get steel that's foldable and wouldn't fatigue, you wouldn't like some of the other behavior parts on it because it's so stiff, right? And it doesn't have any of this. This is called ductility out here, right? So this is in here you're elastic, and here you're plastic in an engineering term. It's not plastic like plastic material, like microplastics. It's plastic in behavior. So you've deformed it, you loaded it up, and it stays a little bit deformed. It's like you take a coat hanger and you bend it, and it doesn't spring back, right? That's plastic deformation. So nylon has a giant plastic range, and it has huge ductility, and it'll go to, like, most of them, the average is over 300% ductility. That is huge. It means it has really good elongation. So you can load it up, it'll stretch and absorb shock. Really good for the kind of stuff we do, right? But the downside is it absorbs shock, but what range is it doing that shock absorption in? It's in a plastic deformation. So it changes shape. That's why it changes shape, is every single time we load it, we take it into that yield plastic deformation state. There you go. So yeah, it did great. Didn't open hard. So you think, oh, nothing's wrong. I can't see anything. Actually wearing your wing out when you do these heavy loaded stuff. So what changes do we see typically? How do we measure this? How do we look at it? This is Jed. Jed and Jeremy both made it into seminars. Jeremy's in the next one. Yeah, this can't be him. So the way we've always been able to measure it is everyone talks about permeability. And it's something that we can measure, and it's definitely a wear thing. They seem to happen in tandem, right? So typically when we're seeing permeability, we start to see distortions. But there's no clean and easy way to measure the distortions. A, because it's in the fibers a lot of times themselves. And so you can't just measure the ripstops. They're not going to, and it's such a small change for a unit, for a small unit, that you're not going to see dimensional changes. So you can't watch it, but you can see that permeability starts to increase. typically what we see is rear riser performance drops when the permeability goes up, and the flare tends to drop, right? Heat does have effect on it. Anything above 180 degrees really does affect the heat strength of nylon. Water changes can affect the weave coating. So when you get a parachute wet, has anybody got a 0 to 3 or an F111 type parachute wet before? Notice some changes. So that change primarily is a calendaring change, right? Because you don't have coatings. When you get fabric wet, you can uncalendar. It starts to lubricate these, and the orientation of that calendaring starts to go away. So that's one change with water that happens. It's not a physical property change; it's a weave change, and that happens to some degrees on coated fabrics as well. So we see all these effects, and we start saying, "Oh my, I've got high porosity." So we all do a porosity test. Oh, it must be it. Must be what's causing it. What we're finding out, and some of this is through research done at some of the PMA, Paragliding Manufacturers Association testing, is that it's not just porosity. In fact, porosity may just be a corollary measure on a lot of this behavior, and that particularly in some of the collapse behaviors and stability stuff on paragliders, is they found that in large part some of the dimensional changes in the fabric play at least as big a role in the continued airworthiness of the wing as porosity does. That was kind of a big thing to realize. It's like, wow. Because what they did is there have been some people that have taken higher porosity wings and put them through certification tests, but in a new condition, an undistorted condition, and they do really well. But then they take a higher porosity wing with a lot of wear on it, and it tends to be the one that fails the certification tests. Downside of this distortion is there's no real objective way to measure it or quantify it. It's just because you don't know the history of the wing. We don't have a great way to measure it. I can't put a strain gauge on your fabric right now. So I can't tell you whether it's deformed completely, but there are a few things we see typically. As the porosity changes, we start to see deformation changes. And one of the things, this is just a corollary, I can't say it's causal because I don't have the research to back it up, but typically when we see the porosity changes, we start to see the changes in dimensional stability. And in our general experience, dimensional changes seem to show up a little bit more on openings, whereas porosity changes tend to show up a little bit more on flare and rear riser performance. Although rear riser performance can also be dimensional as well. Here's a guy flying one of the Odins. I can tell you this is really hard on the fabric. He's really loading it up right here. He didn't have an opening, no reinflations. But that's not an easy maneuver. He's pulling 2 to 3 Gs in the recovery, and then he throws a barrel roll. That's the kind of stuff that distorts the panels. So it's not just us deploying parachutes. It's not just us doing Mr. Bills. The flight loads on these things change the fabric. So we can't measure deflection of the fabric. How do we measure porosity? Right. So some manufacturers have rigged up their own porosity devices, and I think PIA has a method for it. We don't use that. The paragliding world has sorted this in a far better way. It's a standard. Everybody uses the same stuff, and you can buy manufactured devices that are calibrated to the same standard. So that's what we use. We use the PMA tech, and so if you get porosity feedback from us, it's been tested on this particular device, and the tech specs are all the same. They're done under 10 millibars. The surface area is 38.5 centimeters squared. This is all metric because it's European. The volume error is 253 or 250 centimeters cubed, and it's done at a set humidity, and temperature, and you just draw that volume of air through the fabric, and the time it takes is your permeability. So if you get back one and someone says, oh, it took 1,000 seconds, that's good, really good. New fabric will be anywhere from 500 to 2,000. 700 to 200 or 70 to 200 seconds is okay, yeah, it's there, it's good. Midlife, midwear. Again, this isn't going to dictate performance necessarily, but it's corollary, right? And it's the one thing we can measure really well. Obviously, when you start getting down around 30 seconds to a minute, not so good. So good. And we routinely see things way less than 18 seconds. What was the one we had the other day, Jed? It's like 4 seconds, 3 seconds. Yeah, three and a half. And they're surprised. They're really surprised. Well, I don't know. My rear risers aren't flaring good. It's like, well, mesh has about 1.5 seconds. Seriously. So again, that's only part of the equation, guys, right? We can measure this. So when I tell you your wing has like a 10-second porosity, you need to be thinking, okay, yeah, the porosity shot, and it's guaranteed nowhere near the right shape anymore. Those two things need to be in your head.
You tested the results of well before.
0 to 3 CFM, yeah, that's how we know the calendar, the 0 to 3 CFM material, it does change the calendar, yeah, and there is a reduction, almost certainly, but hacking your reserve reduces the strength of, or the porosity of the material. Jumping it really does as well. Again, we don't focus on porosity too much here because, again, it's not the driving factor. It's a correlation, but it doesn't always predict behavior. It tells me a little bit about the wear state of the wing. It tells me a lot about the wear state. And then from that, I can deduce other characteristics, right?
Do you find that when building a experiment, what they can use, like that's that, like tapes, now, obviously, a covering binding standpoint, so that they finish.
Every time that, so here's the thing, it's hard to quantify. It is, unless you disassemble the wing, you can't always quantify it. So like, yes, does water change the tape dimensions? Does it change the fabric dimensions? Absolutely. How much? I can't tell you, because the thing is you would have to know exactly how much it changed from the sewing, first of all. Then you'd have to know how much it changed from the loading, second of all. And then third, you'd have to know how much it changed just from the water. And you can't isolate all three of those, because once the wing's assembled and flown, you can't disassemble it and determine all of that individually. You just know that they definitely change shape over their life. And the harder you are on them, the worse you treat them, the worse the deformations are. I can tell you that we do know from paragliding that the number one way to stretch out a wing and get it out of trim and out of spec is to try to fly it when it's wet. It doesn't show up as much in parachutes, but you can ruin an acro paraglider. You can ruin it. It won't do maneuvers, some maneuvers after this. If you land it in the water and then you pull it up and try to kite it in a stiff wind, they're done. The other thing you can see is you can see some of the, particularly the older acro paragliders, you could see them when they came into service. You could see the ones that had been tumbled. You could look at them and see on that profile. Kevin could tell me, like, oh yeah, this one's been really, really railed really hard. And you could tell which ones had been really G-loaded, because you could start to see some of those deformations. So it's isolating each of those things it's unfortunately not feasible. And that's why we're trying to get with talk about like what can we measure and what correlates to that. But it's important the important part of this is to realize that there's changes happening in your wing through its entire life that need to be there, by the way. We're depending on some of this flexibility of the wing to keep us from having injuries when we have openings. Maybe you didn't slow down when you pitched. maybe didn't do a great job packing, the slider's not on the stops. If we started to use like Mylars and stuff like that that don't have the deformations, the loadings that would occur on your body aren't sustainable long term. So these are things that we need to leave in, material properties that we need in the design of our wings. They have to be there, but they also have cumulative effects over time. So the important takeaway here, right? Higher performance, shorter life. Let's say that again. Higher performance, shorter life. This is even worse when you beat them up in a rough environment. It's not just porosity changes. So we see people that will go, oh, I've got 1,000 jumps on this. I took my old wing, you know, and they talk about a 120. I did 2,000 jumps on it in the desert. Why did this one only last 1,000? It's like, well, it's pretty easy. Hey, you jumped it in Eloy. 1,000 jumps in Eloy. Second is you're loaded at 3.0 on every single jump. And you did Mr. Bills periodically that you're not telling us about. And you kept it in the car. It's just inherently the smaller high performance stuff is going to have less durability. The downside, a Porsche or a Ferrari is not going to drive as far as a Honda Civic, guys. Right? But any day of the week, you walk out and there's 2 cars with a key sit in them. I know which one you're all going to take. We do see that dust and sand has an effect on this. Can't tell you the exact mechanism. My expectation is that it's friction and wear on some of the coatings, because we know that in particular some of these coatings help stabilize the fabric, right? They also help with the porosity. So when we see stuff that comes out from Western US, Utah, Colorado, Arizona, California, places that are dry and dusty, and they're landing in environments that aren't clean grass, we definitely see shorter lifespans on the fabric. You think what? Oh, there you go. Can you think other things? Anyone have any ideas on other things that might cause wear, or anything that they've experienced that gives you this aha moment? Because the aha moment on all of this really is, it's not just porosity. The actual changes in the wing and the shape are at least equal, if not governing some of this behavior. So, questions?